Hey everyone, I hope you've had a chance to watch the video regarding the notes on solving pedigrees. So I've taken those notes and sort of put them here in point form on the right hand side. And so if we look at the first pedigree, what you really need to make sure in order to solve these is you really need to have a firm grasp of the notes and information here for each different scenario in order to ask yourself the right questions when you get to a particular pedigree. So, for example, in the first one, if I look at this, I'm going to notice right off the bat that neither parent has the disorder. And so, yet one of their offspring, one of their children has the disorder. So I know automatically that it's not going to be autosomal dominant simply because you can't skip generations, right? And so that sort of rules out that option. So let's look at it. Is it possible that it could be autosomal recessive? And so autosomal recessive can skip generations. Well, we don't have enough generations here to really understand or see whether or not it skips. Doesn't mean we can't show that it could be autosomal recessive. Um, the individual must have two recessive alleles, and all shaded homozygous are recessive. So there's therefore what, let's say the disorder, you know, throughout this I'll just use disorder. I'll use the letter D or D, right? So in this particular case, this individual has it. So if I'm looking at it being autosomal recessive, then this individual would have to be lowercase d and homozygous recessive in order to have that. Now, is it possible to show the outcome of all these individuals based on it being autosomal recessive? Well, absolutely. In order for the parents not to have the disorder, they would each have to be heterozygous. So dad would be heterozygous, mom would be heterozygous. And we know if we do this Punnett square, and you wouldn't have to do this, but just to show, right, that we would have all the possible gametes showing, and we'd end up with that ratio of 3 to 1. And so there is a possibility. I mean, this pedigree shows perfectly a 3 to 1 ratio, but wouldn't have to show that. But there is a possibility for normal children as well as a child with the disorder. And so, therefore, yes, it is possible to be autosomal recessive. The father would have to be heterozygous. The mother would have to be heterozygous. That would produce both normal children and the potential for a child with the disorder. Okay, how about X-linked recessive? So one of the things I want to emphasize about talking about sex-linked traits, oftentimes when we're talking about autosomal traits, we might just use, if I go back to using the letters that I was showing before, capital D and lowercase d to represent our alleles. If it's autosomal, we just need to sort of show these letters. But if we're talking about an X-linked, and you'll see this when you look at the notes for sex-linked traits, the last set of notes that are posted online under the at-home notes. But when we talk about X-linked or sex-linked traits, what's important here is that we use our chromosomes uh, because what we're looking at is the difference between um, females and males who may be carrying the particular trait or disorder, whichever it is that we're talking about. So, what I mean by that is we want to express females as XX and we want to express males as XY, and then the trait or whatever their genotype is for the particular trait or disorder should be displayed as a superscript, meaning, let's say this female was heterozygous, then we would show it like that. So now we can see clearly we're talking about a female, XX, and we can see clearly what the genotype is that she has for the particular trait or disorder. So we could have a female that is homozygous recessive. We could have a female that is heterozygous, as shown in the first one, or we could have a female that is homozygous dominant, right? All the same sort of notation, but including the X and Y chromosome to indicate whether it's male or female. So, as he said in the video, with males that only have one X chromosome, right, the options are limited in the sense that either they're dominant or they're recessive. They have no other X chromosome to contain two alleles for the particular trait. So as it says up in the notes, males need only have one allele, right? But females would have to have both recessive alleles in order to show a sex-linked recessive or X-linked recessive trait. All right, let's go back to the pedigree problems. Okay, so I'm going to erase a few things here um, and then start the video again to show whether or not it's X-linked recessive or dominant. So if we're talking X-linked recessive, then that means that this would be recessive and this would be normal. And so if we're looking at this individual right here, that's a male, so we have to show XY. And since they have it and we're talking about a recessive, then we have to put a lowercase d with X. Now, if this male has the disorder, then that means that X chromosome had to come from mom. So therefore, mom has to have at least be what we call a carrier for the disorder. And since she doesn't have it, then the other X chromosome must be normal. In the case of dad, dad is normal, not shaded in, and so therefore must also be capital D and a Y. And this is very possible. In this scenario, this dad and mom could produce a male who is normal because he could inherit the normal X chromosome from mom and the Y from dad. This female also could be normal, inheriting definitely a normal chromosome from dad, both of these females. And whether they get the normal or the recessive from mom, they would still be normal. So it's possible it could be sex linked and father would be X D capital D Y and mom X capital D X lowercase d. So mom's a carrier. All right. A carrier is somebody who does not show the disorder but carries an allele for the disorder. All right, I'll pause the video and then set up for X-linked dominant. Okay, with X-linked dominant, again, so now we're looking at this individual male who has the disorder, and if it's dominant, then his X chromosome must be a capital D, and that shows the disorder. Now, if in fact it is autosomal dominant, this individual male got his X chromosome from mom, which means that mom has to have a dominant X chromosome. All right. Now, the issue with a dominant disorder or an autosomal dominant trait is all you need is one dominant allele and you would have the disorder. So if it was autosomal dominant, the mom would have to be shaded in, and she's not shaded in, so therefore it can't be X-linked dominant. No. I won't ask you about Y-linked traits, right? We talked about that the other day in class, so you don't have to worry about that one. So we want to move on to the next one. You can pause the video if you haven't done this. I would hope that you have. But pause the video, give it a try based on the notes from your video, and then start the video to see the solutions. Okay, let's look at pedigree number 2 here. So let's start with the first one, autosomal recessive. Well, if it's autosomal recessive, then since these two parents have it, they would have to both be little d, little d, little d, little d. And in this scenario, every single child would have to have the disorder. There would be no way in which these individuals could inherit a normal allele. So no chance of being autosomal recessive. So therefore, no need to work out the genotypes of the parents. Autosomal dominant. So if we look at autosomal dominant, that would mean that each of these parents would have to have at least one dominant allele, and therefore, in order to have children that have the disease and children that don't have the disease or trait, they would have to be heterozygous. And again, we could look at the Punnett square that would give the 3-to-1 ratio of the phenotypes. And so with a heterozygous cross, we know that you end up with a 3-to-1 phenotypic ratio, which means there's the potential to have individuals with the disease and individuals without the disease. So absolutely possible to be autosomal dominant, and mom and dad are both heterozygous. All right. What about X-linked recessive? Again, if we're talking about X-linked recessive, then what we want to think about is if we're talking about recessive, then it's a lowercase d as a superscript on the X chromosome, and normal would be a capital D. So X-linked recessive, that means that this parent, the father, has only one X chromosome and it must be lowercase d. Mom is, if we're talking X-linked recessive, then she must be homozygous recessive. In this scenario, if it's recessive, mom is going to give all of her sons XD and XD, and dad gives the sons Y. All of the sons would have to have the disorder as well, and so therefore it cannot be X-linked recessive. Finally, X-linked dominant. So in this case, having the disorder would be dominant, and in order not to have the disorder, you would have to have two recessive alleles. So in this scenario, dad is showing the trait or the disorder, so he would have X with a capital D. Mom also would have to have at least one X capital D, and the only way in which these boys would not show the trait is if they are XDY. This is a possibility if mom is homozygous, or sorry, heterozygous. So in this case, dad's going to give the Y chromosome. Mom could give the recessive. So we would have XDY and X little dy, which is possible. And for the daughters, dad is going to give all daughters X capital D, and therefore they would have the disorder. So X-linked dominant is a possibility. Dad would have the disorder XDY, and mom has the disorder and is heterozygous. Okay, so that's all. I'm going to do another video with the solutions to the problems from our notes, which were right here, these take-home practice problems. So if you haven't done those, please give them a go, and then I'll post the solutions.